Hi guys, thank you for coming and staying so late. I'm François Garillot. You might have met me under a different affiliation at the Spark Summit. I'm just an open source contributor of a constellation of projects that is around a firm called Skymind, but all those projects are open source, and then contrary to the word Skymind, they fit on a slide. They don't fit on a slide. And they are helping me for the logistics of actually coming here tonight and actually about coming here tonight and logistics. I have a plane to catch right after the talk, so note that, find me, there's my Twitter handle here. I read all of Twitter and all of my mentions. Find me there, Google me, you'll find my email. Don't hesitate to reach me after the talk. So let's go. We are going to talk about connectivity. There's the idea of is, okay, what is deep learning as a model? As a model, it's a graphical model with that is supposed to represent the composition of functions, and it is trying to use differentiation to see how the results of that composition, ideally the output, is distant from a label that you're providing as part of your data sets. Hence the importance of those supervised data sets. Yes, I'm glossing over details, but basically you're trying to propagate the direction in which you would like to change the coefficients of the parameters of those functions, whether linear or non-linear, to try to reach a result that is closer to the target. And why deep learning? It's because when you stack layers of those graphical models, you get deeper expressivity by massive amounts. The result of the recent success of deep learning, which has been a gigantic model zoo, of which you see just a crude representation here on the left, and it has led to new vocabularies about which kind of model you're trying to represent, going from deep convolutional network to autoencoder, with all of them having slightly different properties and representing slightly different architectures. So it has been said that today, the feature engineering that we were doing in the past, if you're trying to do deep learning, has become actually architecture engineering, where you're trying to solve the problem that you're dealing with. Now, the nice thing about so the deep learning has really come to the attention of people with the release of the ImageNet level dataset, but also with the cat paper by Andrew and Google. There were those news in the field about how now we know how to recognize cats from dogs. And the AlexNet really changed that and made convolutional networks explode. And one of the latest results that I'm really fond of is that last week Microsoft had a team that had speech recognition at parity with humans, or better than humans, which means that Skype is now going to be able, soon, going to be able to translate a sentence that you would pronounce in Spanish to one of your interlocutors that would receive it in Russian. And that has led to some industrial interest. And among this industrial interest, there's a few examples that I'm really interested in. Now, you know that autonomous vehicles are the future and they're going to be on the street tomorrow. But there's, we know the usual guys that have been paying attention to this field, but I wanted to mention a couple of the outsiders that have even more interesting ideas. There's a very expensive piece of equipment that you need to put on an autonomous car these days to make it run as the big guys, Uber, Google, and the others, Tesla, are doing it, which is called a LiDAR, which is a very expensive laser to basically be caricatural about it. TriData and Komai are actually looking at retrofitting cars with the ability to drive autonomously and to do it without that LiDAR, which means that they depend highly on cameras and therefore on image recognition. And they depend on this running at scale and really, really fast. Another application is drugs discovery that come, among others, from a paper by Ben Fryer at Toronto. He has created a startup, Deep Genomics, out of that. But Bayer, a huge pharmaceutical company, is looking into this. And there's even more applications of a different kind of neural network that is really good at processing time series or time series-like signals for predictive maintenance when you have a lot of equipment in the field. So that in the end, there's a lot of hype at the moment saying that deep learning is going to bring us a human-level AI. Now, if I put myself in the shoes of an enterprise that is really of a large size and is looking to make money off of the deployment of such a model, I'm thinking, yeah, the singularity is not going exactly to pay my bills at the end of the month. I'm taking the approach of optimistic pessimism. So prove me that it really works really well, and I'm going to need Philip to enter his password or to prove, no, that might come back, okay. Except I have gone through 20 slides. Phil, for the next speakers, you might want to remove that sleep thing. The optimistic pessimism is the idea that, okay, give me a model that is proven and known to work on known data, and I'll pay attention to that specific application. Now, the idea is that Nick has done me a great favor at presenting the different steps in the deployment of such a model. So what if I wanted to deploy that? Well, I can use TensorFrames if you've been at the Spark Summit. But at the Spark Summit, you've noticed that TensorFrames is really useful and well known, and the demo was mostly about applying already pre-trained models to whatever data you were feeding in. Now, you can expand it a little bit, and we're going to go into that. But the training, it tends to require a lot of data. But remember, in my mind, I'm a really, really big enterprise, and I have a lot of data. I'm a telco, for example, and my data is inside my silos because of regulation. I cannot get it out of my company. My data is private data from a customer, which is highly protected, so I'm not giving that to a contractor easily. So applying the model is not going to be done by a pre-trained model. I'm going to be trying to develop a standard architecture, but on my own data. Okay, training tends to require a lot of data. You notice a slight R here. It means that I'm slightly omitting to mention some research results that are absolutely fascinating. Look it up on your own, or ask me for the limits of that. But applying pre-trained models is not really the technical challenge for me as a big enterprise. I have a lot of data. I'm trying to train, really. But how do I train? Well, I look at the technology in the field, and I find articles that are pretty recent. This is August, benchmarking the state-of-the-art deep learning software tools. And I think, oh my God, I'm going to read this 6-page paper and I'm going to be done. Except all the benchmarks that are in there are not distributed. Oops. Okay, I have really a lot of data. I'm going to need to run the training of that distributed all for 6 years. I don't really have 6 years. So, okay, so there's cloud solutions. That's easy, right? Amazon has just updated its new Amazon GPU instances. I'm just going to deploy that on the cloud, okay? It's fantastic. You can have as at least 16 GPUs per machine and have turnkey startup of machines. It's going to be fantastic. Except the economics of all of that are not really good. That's what you see on the left here. So 96 GPUs trained for 6 days, 144 hours at $15 an hour is $12,960 just to reproduce a research level result on a recent paper. And that's to reproduce the paper, not to experiment with it. Okay, that's a little bit big as a budget to give to my data science team for just a small, teensy tiny experiment. But I can notice and still read what comes out of NVIDIA and notice, hey, they have this GTX 1080 that gives me a heck of a lot of computing power per watt. That's quite interesting. So the GTX, NVIDIA sells a big box that is pre-configured for everything, but it costs around 130K, and I don't really have 130K, but I do have a cluster. I do have a cluster with machines, and I can put 1080s on it. So the distributed context has been solved by 5 companies in the world, which means it can be solved. And if I solve it on my cluster, I have one. Isn't that fantastic? Let's use TensorFlow. In version 0.8, they have released distributed training. Oh wait, TensorFlow on the distributed training might not be what Google runs in production. Oops. Okay, let me look at it myself. It's essentially distributing SGD. This should be a GIF that actually shows you how you're descending on that. But the challenge is the networking pattern of already used communication. And DeepLearning4J is the first commercial grade, open source, distributed deep learning library written for Java and Scala. A lot of components. The idea is that we have a C++ library that lets you access all the linear algebra. We have one thing which is interesting even to people not doing deep learning, which is ND4J. It's a NumPy for the JVM that lets you do arbitrary computation. Loading a library called DataVec, and then DeepLearning4J, which is the core of our deep learning offering, and Scalet, which is a reimplementation in Scala of Keras, so that you can get the use of deep learning without spending a lot of time deploying the models. We even have a recent reinforcement learning, again this was supposed to be a GIF, reinforcement learning library that use asynchronous arithmetic methods, and a number of bottlenecks that I would like to solve in Spark, if you're to make that work with Spark implemented as a synchronization and parameter server engine. But a lot of things that you may have noticed is that binary format support in Spark is not absolutely optimal. The network stack could be faster. Lightband and Skymind have written the networking stack using Aaron and seen at 10x. You might want to pay attention to that. And there's more, and actually IBM Japan has been doing a lot of work on this. If you want to contribute, help us discuss, there's an issue around the use of ND4J for things that are not even deep learning, which is Spark 6.4.2, better linear algebra than Breeze, and there's a lot of opportunities for collaboration, and all of our resources of our code is open source. Thank you very much.
Excellent work.